Welcome to chemistry session. In this chemistry class, I'm going to discuss about bonding in metals. Coming to the theories of bonding in metals, any of the theory of the bonding in metals, they must account the characteristic properties like high luster, complete opacity, high thermal and electrical conductivities, applicability of the Ohm's law, applicability of Wiedemann-Franz law, the ratio of thermal conductivity to electrical conductivity, variation of resistivity in presence of external magnetic field. In order to account these observed properties of the metals, there are several theories which have been proposed and they have discussed in this bonding in metals. Already the valence bond theory was discussed and free electron theory, the second one. And the third theory is band theory of solids. Coming to the band theory of the solids, the free electron theory described earlier was successful in explaining some electronic and thermal properties of the metals, namely specific heat, paramagnetism, all these were discussed. And there are other properties which couldn't be explained by free electron theory. For example, the theory fails to explain it couldn't explain why some metals are good conductors, some of them are insulators, and some of them are semiconductors. And the basic flaw in the electron theory is that it doesn't take any account the wave-like properties of the electron. It assumes only the conduction electron experiences a constant potential throughout the solid. But in a crystalline solid, X-ray diffraction studies reveal that the a periodic property of the positively charged nuclei through which the electrons move, the potential of the electron at positive ion core is zero, and the potential is maximum between the two ion cores. So this variation in potential energy is periodic and varies in accordance with the lattice periodicity. So the one-dimensional model of the variation of the periodic potential can be represented. So, in order to study the motion of the electron in such periodic potential, the resultant energy is approximated in the periodic repetition of the potential. So, there are many assumptions, Kronig, Penny model, all these have been given. So, the potential energy of the electron in the linear array of the periodic nuclei, it consists of the square cells. At the bottom of the well, the electron is assumed to be vicinity of the positive ion core. And there are some of the assumptions as such. So with these assumptions, this Chronic and Penny obtained one of the dimensional solid, the following important conclusions. What their conclusions were given are the energy spectrum of the electron consists of bands of the allowed energy separated by regions. Width of the allowed energy band increases with energy. And therefore, it suggests that energy of an electron in periodic potential is intermediate between that of free electron and a bound electron. In a free electron, the energies levels are like whereas they're bound in the electron and the energy levels are discrete. So allowed energy levels for the free electron, bound electron, and an electron in the periodic table can be shown. So before that, we see here the periodic table. So how the metals, the red color ones are all the metals, and the yellow color ones are the metalloids, and the blue ones are the non-metals. These conduct the electricity, and these non-metals do not conduct the electricity, insulators. And these non-metals, they conduct during some conditions, doping, such conditions, they conduct the electricity only with the some doping or the external flow. Any of the impurities are doped, then you get the conductivity. Now we'll see about the metals, non-metals, metalloids theories. Yeah, as of previously, we have discussed about the free electron theory, valence bond theory, and today's class I'm going to explain you about the valence bond theory, the molecular orbital theory. Two atomic orbitals of equal energy combine together to form combine together to form two molecular orbitals by LCAO method. Similarly, when three atomic orbitals are combined together by LCAO method, three molecular orbitals are formed. The energy of these molecular orbitals are very close and appear as continuous energy bands. Hence, this theory is called band theory. Two atomic orbitals of equal energy will combine together to form two molecular orbitals. That is LCO method. Similarly, when three atomic orbitals combine together by LCO method, three molecular orbitals will be formed. So here the energy of the molecular orbitals close and they're continuous, just like the continuous bands. So this is the band theory. So yeah, here it was explained for the example lithium crystal. If you take, if n number of the lithium atoms are allowed to combine, they will form three energy bands. So 1s band, it is formed by combination of n number of 1s, two atomic orbitals. This band is completely filled. So it is a non-conduction band. If it is completely filled, there is no place for movement of the electrons. So there is no conduction, it's non-conduction band. And you take lithium 1s2, 2s1. So here you take 2s band. It is formed by combination of 2s1 orbital, 2s1 atomic orbital, and this band is halfly filled. So it is conduction band. So once if it is halfly filled, you have a space for the movement of the electrons. If it is completely filled, there is no place for the movement of the electrons. So that becomes non-conduction. There is no movement of the electrons. And thereby, you don't get any conduction. And for 2s, if there is movement, because of halfly filled, you get space and there is movement. That is the conduction band. So the upper half of the band is empty, while lower half of this band is completely filled. So 2p band, it is formed by the combination of n number of 2p subshells. This is called empty band and it has no electrons. So 1s band is a combination of n number of 1s2 orbitals and it is completely filled non-conduction. 2s band is combination of 2s atomic orbitals. A band is halfly filled, so it is a conduction band. The upper half is empty while the lower half is filled. So there can be a movement from filled to non-filled. N2p band, it is formed by combination of n number of 2p subshells. 2p band is formed by combination of 2p subshells. This band is called empty band. It has no electrons. As I've told you, this molecular orbital theory, two atomic orbitals of equal energy combine together to form two molecular orbitals by LCO method. And here as three are combined to form three molecular orbitals. We have discussed. Energy of these molecular orbitals closer appears as continuous energy bands. Hence you call it as a band theory. Why you call this one as a band theory? It is just because they are continuous. So allowed energy levels for free electron, bound electron, and electron in the solid. The wide, the you can see the energy levels corresponding to the free electron, bound electron, electrons in solid. So consequences of the band model is the apparent success of the band model is its ability in explaining the behavior of solids, consequent division of materials into conductors, insulators, semiconductors. The band consists of valence electrons is called valence bond, while the immediate next band of higher energy is called conduction band. And in conductor, either the valence band is partially filled or there is an overlap between filled valence band and empty valence band. In either case, the electrons are free to move in a band and thus conduct the electricity. So arrangement of bands in the first group elements like sodium, potassium, arrangement of bands in the second group elements like calcium. So if valence bond is completely filled and the conduction band is separated by a small forbidden gap, thermal energy may be sufficient to cause excitation of electrons from filled valence bond to empty conduction band. The material is said to be the semiconductor. So the behavior of the semiconductor differs from conductor in its temperature dependence of the electrical conductor. Whereas in a conductor, yeah, we'll see the lithium crystal after explaining this one. And the behavior of the semiconductor differs from that of conductor in its temperature dependence of electrical conductivity. In a conductor, an increase in the temperature doesn't increase the number of conducting electrons, but it increases due to the collisions between the conducting electrons. As a consequence, the electrical conductivity of the conductor decreases with increase in temperature. Okay, even the increase in temperature causes increase in the number of excited conducting electrons in semiconductor. As a result of this, electrical conductivity increases with increase in temperature of the semiconductor. Oh, finally, filled valence band is separated from the empty conduction band by a large forbidden gap. It is almost 5 electron volts. The example will lithium, n number of lithium atoms allowed to combine, they will form 3 energy bands. As I've told you, one is formed by combination of n number of 1s2 atomic orbitals. So the band is completely filled, no conduction, no place. And for 2s bands, it is formed by combination of n number of 2s1 atomic orbitals. And this band is half filled. So it is the conduction band. It is the conduction band. So the upper half of this band is empty while the lower half is completely filled. This gives a great arrangement of the conduction, half filled. So the electrons can jump from filled side to the unfilled side. There can be a movement and there can be a conductivity. And coming to the 2p band, how a 2p band is formed. It is formed by combination of n number of 2p subshells. This band is called empty band as it contains no electrons. You can see here the gap between 1s band and 2s band is called forbidden gap. As energy gap is very high here, energy gap is very high, so electrons cannot be performed. They can be promoted from lower 1s band to the higher 2s band. See, the gap between 1s band and 2s band is called the forbidden gap. As the energy gap is high, the electrons cannot be promoted from lower 1s band to the higher 2s band. The level below which the all bands are filled are called as the Fermi level, and it increases within a band or in the gap between the two bands. Now, coming to the insulator and these are the semiconductors theory The properties can be explained for the conductors, insulators, and semiconductors. This theory explains easily the properties of the conductors, insulators, and semiconductors. Yeah, one level, two, and this is three. This is first, second level, and this is three levels. Here you're having four levels, atomic orbitals, and these are five energy levels. Let's see the conduction. Yet 30. You can see the bandwidth, energy band. So some of them are filled and some of them are empty. Bonding molecular orbitals and anti-bonding molecular orbitals. Yeah, 2p you take. This is the generalized diagram for the number of orbitals and the bonding molecular orbital and the anti-bonding molecular orbitals at the energy bands. Here we'll see for lithium, one atom, two atoms, three, five, so on. See, if 2s, there are many atoms and the 2s they combine. And here 2s combine, here all the same type. How many ever the atomic orbitals combine, the same number, the molecular orbitals are formed. Now here, you can see here, lithium 25. All the 2s orbitals come into one place. And 2p orbitals, for one lithium, 2, 3, all the 2p are going to one side. Here, different levels of the 2p in the lithium crystal. And here you can see the total lithium, one is the band levels, two is band levels, and here you can see the 2p band levels. And atomic orbitals on combination, you're getting two types of orbitals, bonding molecular orbitals and bonding anti-bonding molecular orbitals. This complete one is one band and this complete one is another band. This band is formed due to the combination of the molecular orbitals. This band, it is formed due to the combination of the anti-bonding molecular orbitals. So this is the valence bond and this is the conduction band. Here it is halfly filled. So you can go for this one, you can call it as a conduction band. Now what is the Fermi level? It is the hypothetical energy level above which the probability of finding electron zero at 0 Kelvin. And in metals, highest occupied molecular orbital in the valence band at 0 K can be considered as Fermi level. In the metals, highest occupied molecular orbital in valence band at 0 K can be considered as Fermi level. In insulators and semiconductors, it is found in the band gap. So Fermi level is the energy level above which probability of finding an electron zero at 0 K. In the metals, the highest occupied molecular orbitals in the valence band at 0 K can be considered as the Fermi level. So, however, in insulators and semiconductors, this band gap can be found. You can observe electron energy. And for metals, this is the way they overlap. Valence bond, conduction band, both of them overlap. So there is no gap between these two bands. Therefore, the electrons move from valence bond to the conduction band. They keep jumping. The energy gap is very less. The band gap is very less. So it makes easy for the travel of the electrons. And thereby you can observe the conduction in the metals. And coming to the semiconductors, the conduction band is almost distant. And this is the valence bond in this. The energy gap, this is Fermi level. The energy gap is very, very less. So almost there is a gap, but it's less. So electrons jump from semiconductors to the conduction band. From here, semiconductors, they jump from here. They jump from valence bond to the conduction band. And the Fermi level you can observe it's less. Here, the gap is less. So during the doping condition or during the addition of some elements, extrinsic conduction or intrinsic conduction can be promoted here. And thereby normal conditions there is no conduction, but during special conditions that is doping, there is conduction. This is about the semiconductor. Now we'll see insulators. There is a lot of band gap between the valence bond and the conduction. So therefore, once you do doping or whatever you do, there is no chance of electrons jumping from valence bond to the conduction. Here, this is the conduction band and this is the valence band. Semiconductors Fermi level, the gap is more between this conduction band and valence band. Therefore, the jumping is difficult. And coming to the once if you see in this metals, there is complete overlap. So semiconductors, a little gap will be there. Now we'll see what are insulators, what, how is a metal, what is a semiconductor, and what are insulators. All these properties can be discussed. So previously in free electron theory, all the properties were not discussed in detail. And even in the valence bond theory, it was not discussed in detail. Now I'm going to tell about the properties about the insulators. Insulators completely filled valence band. Insulators, why? They don't conduct the electricity. They cannot conduct the electricity, insulators. They have completely filled valence band. Energy difference between valence and conduction band is more. Due to more energy gaps, the insulators cannot conduct the electricity. And valence band is separated by empty conduction band, and the forbidden gap is more. And it is more, and the thermal energy will not be sufficient to cause the excitation. That is not sufficient for the excitation of the molecules. So the filled valence band is separated from empty conduction band by large forbidden gap here. Here there is large forbidden gap between the valence bond and that is separated from the empty conduction bond. And due to this gap, the large forbidden gap, it is almost 5 electron volts or more. And thereby, this insulators, the thermal energy will not be sufficient to cause excitation of electrons from valence bond to the conduction band. Here, here, it is more than 5 electron volts or more, and thereby the thermal energy will not be sufficient. Thermal energy will not be sufficient to cause excitation of the electrons from valence bond to conduction. Hence, the material it will not be able to conduct, and it is called insulator. Energy bands in semiconductor, and this can be here. They can be depicted in this way. Now, conductors. See, there is less energy gap between the valence bond conduction band for the conductors. I've told you previously showing the diagram. There is less energy gap between the valence bond and the conduction. Valence bond and conduction band are overlapped. Valence bond and the conduction band are overlapped. Electrons can easily move from valence bond to the conduction band. Electrons can easily be move from valence bond to conduction bond. Thereby, uh, you can see the movement of the electrons, which is called electricity. They can conduct the electricity. In other case, here I've told you the electrons are free to move in the bands and they thus conduct the electricity. The movement is very easy. So it is able to, this theory is able to explain the solids consequent, how the metals are these conductors. And this band consists of the valence band, yeah, consists of the valence bond, valence electrons. It is the valence bond. Valence bond consists of the valence electrons. While emit the next higher energy is called the conduction band. Yeah, in conductance, in the conductors, the valence band is partially filled, and therefore there is overlapping here. There is overlapping. So in conductors, the valence band and the empty conduction band, you as shown in the figure. In these two, the electrons are free in the band and thus they conduct the electricity. So the both of them they are overlapping and the gap is almost nil. It's not at all there. There is no Fermi level here and overlapping you can see, and therefore there is electron movement and there is free movement, and therefore the band it conducts the electricity. Now we'll go for the semiconductors. In semiconductors, the valence band is completely filled and the conduction band is separated. A small forbidden gap, which is having small forbidden gap. Here the thermal energy is sufficient. It is having very less forbidden gap and the thermal energy is very less. It is sufficient to cause excitation of the electrons from filled valence bond to the empty conduction band. So thermal energy may be sufficient and to cause excitation of the electrons from filled valence bond to the empty conduction band. So the material here can be called as materials is said to be the semiconductors. Whatever is having this type of bands, that is the semiconductors. So in the conductors, an increase in temperature does not increase the number of conducting electrons. So in the metals, that is in the conductors, in a conductor here. So you can see in a conductor, an increase in temperature in conductors, that is metals, increase in temperature will not increase the possible collisions. It will not increase here. The temperature does not increase the number of conducting electrons, cannot increase the number of conducting electrons, but it increases the possible collisions between the conducting electrons. Therefore, the electrical conductivity of the conductor decreases with increase in temperature. Because increase in temperature will not increase the conducting electrons, but increases the collisions between the conducting electrons. Collisions takes place once if you increase the temperature for this metal, for the conductor, collisions will take place between the conducting electrons. Therefore, the conductor conductivity decreases with increasing in temperature. And in contrast, increase in temperature causes increase of the number of excited conducting electrons in the semiconductor. So for semiconductors, that is the reverse case. For the conductors, as the temperature is increased, collisions increase and conductivity is decreased. But semiconductors, that is the reverse case. As you increase the temperature, number of excitations of the electron will increase, and the exciting conducting of the electrons is seen in the semiconductors. And therefore, the electrical conductivity increases with increase in temperature for semiconductors. I have already explained you about this insulators, completely filled valence bond. Having the completely filled valence bond, and due to more energy gap, the valence conduction band, cannot connect the cannot, there is no movement of the electrons, conduction of the current. And due to the more energy gap, the insulators cannot conduct the electricity. And coming to the conductors, less energy gap is there between the valence bond and the conduction bond. So valence bond and the conduction bond are overlap. And therefore, the electrons easily move from valence bond to the conduction bond. So you can see the conduction of the electricity. Semiconductors, there is less energy gap between the valence bond and the conduction bond. Promoted electrons in the conduction band and unpaired electrons in the valence band cannot conduct the electricity. So probability of promoting electron arises with temperature. The conductivity of the semiconductors increases with the holes. See, hole is formed in the valence band due to transfer of electrons from valence band to conduction band. There is a hole is formed in the valence band due to the transfer of electrons from valence band to the conduction. So hole is a positive charge. And as a hole is formed, you can there is a chances for the conduction. Told it clearly. This is the insulator. You can see the conduction band. Here is the valence band. The gap between these two bands is very fine. And for semiconductors, this is the conduction band, this is the valence band. The energy gap between these two is a bit lesser. This band gap, Fermi level, you can get it. And for the conductors, you see the conduction band and the valence band almost are overlapping. The bond gap is negligible, still decrease. So electrons can jump from valence to the conduction band. And here in the semiconductors, slight gap of holes are chances of holes are expected here. And the holes are the positive charge ones. So while doing the doping, the electrons can come and occupy the holes in this semiconductors. So due to the less bond gap, the electrons, they have, once if a doping is done, the valence electrons have chances to jump from valence bond to the conduction band. Now we'll take for the insulators. The band gap is very large, and therefore the chances for the jumping of the electron from valence bond to conduction band is almost negligible, and therefore there is no movement of electrons from valence bond to the conduction band, and therefore there is no conduction of the electricity. There is no movement of the electrons, and therefore non-conductance you can observe. As I've told you, conductors, with the increase of temperature, collisions increase and the conductance decreases. And for semiconductors, if you see, as the temperature increase, the reverse happens. What is that? Once if you increase the temperature, the collisions increase, that there is chances of electrons to jump from the valence. They gain energy and there are chances for jumping of the electrons from valence to the conduction. Okay. So this is the pictorial representation for the insulators, semiconductors, and conductors. As I've shown you in the periodic table, the elements, what the first, the starting is block elements, all these are metals, that it, and semiconductors, the fourth group elements, and from 6, 7, you have the non-metals. Yeah, insulators, you see how nice the picture, the completely filled valence bond. More energy gap with the valence bond with the conduction. So all same type of orbitals to come to one place, valence bond. This is conduction band, large energy gap. This is Fermi. Due to more energy gap, insulators do not conduct the electricity. Conductors. Less energy gap between the valence bond conduction bond. So valence bond and the conduction band overlap here. This is the valence bond in metals, and this is the conduction band in the metals. So valence bond, conduction bond, Fermi level, no Fermi level, almost everything overlap. So less energy gap between the valence conduction band, valence bond conduction band, that can overlap electron easily move from valence band to the conduction. They conduct the electricity. Now coming to the semiconductors, there is less energy gap between the valence bond and the conduction band. So electrons are promoted in the conduction band and unpaired electrons in the valence bond conduct the electricity. The probability of promoting electron rises with temperature. The conductivity of the semiconductor it increases with temperature. See, as I've told you, the hole is formed in the valence bond. You have to transfer electrons from valence bond to conduction. This is the valence bond. The electrons pass from valence bond to conduction. When the energy is increased, the valence bond, electrons jump from here to here. Once electron, the minus charge is jumping from valence bond to conduction bond. Here, when minus is transferred, one plus is formed. Plus is nothing but a hole. Hole is formed. So, due to less energy gap, this valence bond, conduction band, they promoted the electrons in the conduction band and the unpaired electrons in the valence band conduct electricity. So probability of promoting electron rises with the temperature. The conductivity of the semiconductors increases with temperature. The Fermi level, small energy gap, conduction band valence. This is the way the semiconductors conduct the electricity. So here for semiconductors, as the temperature increases, what happens is the number of collisions also increase. They gain energy. Therefore, they they jump from the valence bond to the conduction bond. And in the conduction bond, you get once an electron is shifted from valence bond to conduction bond, here positive charge is formed. This electron is minus charged. Once a minus is shifted from one place to the other place, there you can see a hole. Hole. That hole is a positive charge. So this is an indication for the conduction of the hole formation. So this is the band theory. It is an apparent success of the band model. It is its ability it has the ability of explaining the behavior of the solids, consequent division of the materials. So the what the consequences of the band model we have seen, allowed energy levels, and the bound electron in the solid, the widening energy levels in the energy bands continues, and the proximity of the interacting atoms we have seen. And this is a great success of the band model. This is the band model. It's a great successful model. Why? Because it is able to explain the uh, behavior of the solids, division of the materials into conductors. Yeah, thus theory it is able to give a clear cut division of the materials into conductors, insulators, semiconductors. This band consisting of the valence electrons is called valence bond. Immediate the next band of the higher energy level is a conduction band. Everything was explained in this theory. In either case, the electrons are free to move and thus they conduct the electricity. So the valence bond, it's basing on this forbidden gap, they're able to explain the three types of materials and their conductance. And why due to that gap, what it's happening, how an insulator behaves, why a semiconductor, how it behaves, and the delta energy it is less than 3 electron volts for semiconductors. And for insulators, the energy gap delta is more than 5 energy. See, for insulators, it is delta is more or equal to 5 electron volts. And for semiconductors, the delta is less or equal to 3 electron volts. So 3 electron volts is less, and thereby the electron can easily jump. Once if the temperature increases, somehow gains the energy, and there is conduction of the current. Okay. So today's class, this band theory, uh, I hope everybody have understood clearly. So what we have discussed in this band theory is about the molecular orbital theory. See here different metals, molecular orbital theory, or you can call it as a band theory, bonding in metals. The third theory, it is the band theory. Here we can see the metals, non-metals, and metalloids in the periodic table, how they are classified depending on their conduction. S block elements except of the hydrogen, total S block elements, D block elements come under the metals. Even the third group elements except of boron comes under the metals. And in the fourth one, tin and lead. The group bismuth, polonium, and sixth group. All these are the metals. And the non-metals, metalloids are boron, silicon, germanium, arsenic, antimony, tellurium. And the non-metals are all the p block elements. Most of the p block elements, the 3/4 of the p block elements, comes under the metalloids. And the molecular orbital theory, LCO theory, how the molecular orbitals formed is explained in this band theory. The lithium crystal is taken example, and the 1s band how it is formed, a 2s band how it is formed, a 2p band how it is formed. All s orbitals give s band. All the 2p orbitals give 1s orbitals give 1s band. 2s orbitals combinedly give 2s band. And 2p or n 2p orbitals give 2p band. Now, molecular orbital theory, what is a forbidden gap? We have explained. The gap between the 1s and 2s is the forbidden. What is a Fermi level? The level between which all bands are filled are called Fermi levels. The level below which all the bands are filled is the Fermi level. It arises within the band or in the gap between the two bands. This way, the total molecular orbital theory is explained basing on the example of this lithium metal. What is a Fermi level? The diagrammatic representation is given. So it is a successful theory which has classified the materials into 3 different types. Division of the materials into conductors, semiconductors, insulators. What is insulator, what are conductors are explained. I hope everybody have understood today's class. The properties of the insulators, conductors, semiconductors. Thank you, everybody.